we will see the problem example 7.1. Sketch the Bode plot for the following transfer function and determine the system gain k for the gain crossover frequency to be 2 radians per second. Gain crossover frequency to the 2 radians per second. What is the PM for the value of k, that is phase margin? What is the value of k for the gain crossover frequency to be 5 radians per second? For this value of k, what is the phase margin? So g of s and h of s is given with the k into e to the power of minus 0.1 s divided by s into 1 plus s into 1 plus 0.1 s. So for the given g of s, h of s, the sinusoidal transfer function is g of j omega h of j omega is equal to k into e to the power of minus j 0.1 omega j omega 1 plus j omega 1 plus j 0.1 omega. So here considering k as 1 and draw the Bode plot taking k is 1, and from the Bode plot calculate the value of k for gain crossover frequency to be 2 radians per second. Now here one unexpected term is the e to the power of minus 0.1 s. How you can deal it? The effect of time delay Td is to add a phase equal to minus omega Td into 180 degree minus pi along the curve. The effect of time delay Td is to add a phase equal to minus omega into Td into 180 degree by pi along the curve. So the time delay Td has an effect to add a phase equal to this value minus omega Td 180 degree by pi along the curve. This phase, when there is a term of time delay, then you have to add this much phase to along the curve. Now the factor e to the power of j omega Td correspond to the time delay. So here e to the power of j minus 0.1 s. So here when you are comparing it or e to the power of minus j 0.1 omega. Now Td is here, Td is point, when you are comparing Td is 0.1. When you are comparing this and this, here Td is 0.1. Okay, in that case 180 degree by pi into omega into Td, that is equal to Td is 0.1 into omega into minus 57.3, that is 180 degree by pi, that is equal to angle of 57.3 into omega into 0.1, that is equal to minus 5.73 omega degree. So here when you are calculating the factors, k you are considering it as 1 is e to the power of a term is there, then 1 by e to the power of j is 1 by j omega, then 1 divided by 1 plus j omega, 1 divided by 1 plus j 0.1 omega. So now e to the power of minus j 0.1 omega. So corner frequency none, asymptote log magnitude characteristics 0 dB at all frequencies. When you are getting a time, when you are getting time delay factor, it offers 0 dB at all frequencies, and the phase angle characteristics, that is already we calculated with these expressions. minus omega TD into 180 degree pi, that is equal to angle of minus 5.73 omega degree will be added, or phase angle, this will be is the phase related to this, but it will offers 0 dB to the magnitude. 1 by j omega, 1 by j omega, when you are calculating the 1 by j omega, 1 by j omega, we need to go back. Yeah, 1 by j omega, when 1 by j omega, it is having a slope of minus 20 dB per decade, and it grows to omega is equal to 1 at 0 dB. Okay, and angle is, you can see the angle is, in this case minus 90 degree. Angle of this is minus 90 degree. So here corner frequency is not the straight line of constant slope minus 20 dB per decade passing through the 0 dB line at omega 1 radians, and angle is constant minus 90 degree. Now when you are calculating 1 by 1 plus j omega, here when you are calculating, it is in the form of 1 divided by 1 plus j omega t. T is 1. So the corner of omega 1 is equal to 1 by t, that is equal to 1. And here you know that till corner frequency it is 0. After corner frequency it is minus 20 dB per decade. Straight line of 0 dB till omega 1 corner frequency. A straight line of minus 20 dB per decade when omega greater than omega 1, that is 1. And here as you can see that till at corner frequency minus 45 degree, minus 40 degree, and phase angle varies from 0 to minus 90 degree. Same thing happening here also, only difference is corner frequency, 1 divided by 1 plus 0.01 omega. Here this is in the form of 1 plus j omega t. T is 0.1, so omega 2 is 1 by t, so 1 by 0.1 is equal to 10. Until this corner frequency it is 0. After this corner frequency it is minus 20 dB per decade. Here also phase angle varies from 0 to minus 90. At corner frequency it is minus 40 degree. Now when you are drawing like that, and here 5 radians is in a question, it is given as 5 radians, 2 radians, or you got it. And the first corner frequency is 1, so it should be, and again the total angle, how it is calculated. The angle can be calculated. Pi is equal to 1 by j omega offers minus 90 degree. This one offers minus tan inverse of omega. This one offers minus tan inverse of 0.1 omega. And first one is angle of e to the power of minus j 0.1 omega. It will offers minus 5.7 omega. So for different omega, you need to calculate the angle. So when you are calculating for omega is equal to 0.1 and 1, 2, 5, 10, all you need to calculate the angle. So you are getting like this different, and you have to start drawing the curve. You need to start drawing the curve. So now starting from 1 by j omega is not having a corner frequency, so we will draw this one, and it will cross omega is equal to 1, and next corner frequency is omega is 1 only, so we can draw till omega is equal to 1 with a slope of minus 20 dB per decade. So here this is omega is equal to 1, this is 0.1, then here it is 10, this is 100. So till 1, yeah, till 1 it is minus 20 dB per decade. Till 1, this line should pass through this one. Okay, then after that 1 till omega 1 this offers, till 1 this offers, till 1 this offers 0. After that it gives a minus 20 dB. So previous minus 20 dB, this also minus 20 dB. So we are getting after 1 this will be 40 dB till where? Till 10. So this is 1 till here it is minus 40 dB. After that from 10 onwards it is minus 60 dB. Now the corresponding angle also you need to draw. Very carefully you have to draw it. So this all you take a semi-log graph. All the students you should practice with the semi-log graph. You need to practice it. Okay. Now semi-log graph you should practice it. Yeah. Now for next question is, yeah, if the gain crossover frequency is 2 radians per second, then find the value of k. What is the PM for this value of k? So now this is 1, this is 2. At 2, this value is 12 dB. 12 dB. Okay, 12 dB. So we can say that 20 log k is equal to 12 dB. So k is equal to 12 by 20.6. K is equal to 4. So when it is gain crossover frequency is 2, then k is equal to 4 dB. When k is equal to 4, what is the phase margin? The phase margin is plus 3.9 degree from minus 180 degree to this line. Now next question is, what is the value of gain crossover frequency at 5 radians per second? So this is 2, 3, 4, 5. 5 at 5, the distance is 30 dB. So in order to make gain crossover, this graph should be shifted so that it passes through this way. Similarly, for a gain crossover 2, this graph should pass through 0 at 2. Now the difference is 30 dB. So it is, you should consider as plus 30. So you can see 20 log k is plus 30 dB. Log k is 30 by 20, 1 plus 1.5. K is log inverse of 1.5. That is equal to minus 31.5. Now for k 31.5, at this point, the phase margin is below the 180 degree. So the phase margin is minus 43.8 degree. So when you are getting like that, the system is unstable. So if you are doing like that, that means if the gain crossover frequency is at 5 radians per second, that time it is unstable. Otherwise, previous case, it is stable. So all of you use, if you can use semi-log sheet, use that and draw it and understand this problem. Draw in the semi-log graph sheet like this only. Or if you are not getting the semi-log sheet, whenever you are getting an opportunity to get it, immediately you purchase some around 20 sheets and practice on semi-log sheet.